Thanks everyone for joining us today in our May meetup. For those of you who are here for the first time, we keep running those every month. So check out our meetup page. And we do always present some exciting topics in the space of data science, in the space of generative AI lately as well, and always invite speakers that have exciting topics to share. And we do have, of course, an exciting agenda for today as well. We're gonna start actually with a brief lightning talk from Chris. Chris is preparing some great content right now, so he wants to give you a quick peek into that, briefly talking about generative AI parameter efficient fine-tuning called PEFT, a little bit the difference between the prompt tuning and other techniques, and also a little bit around reinforcement learning from human feedback. We will have a larger session on this in next month meetup, but just to give you a quick sneak peek today. And then we do have our speakers here today, Sonali and Anjan from AWS, who are going to present how to implement intelligent document processing with AI services, and also, of course, Gen AI. And we do have Dilshad today as well, who's going to talk about reinforcement learning, this time to perform portfolio optimization. Super exciting. That will include Ray as well with SageMaker. So I'm looking forward to our talks today. Chris, anything else you want to share?
No. What do we know what we have lined up for next month, by the way?
We do have your session, so the extended lightning talk, and we'll update soon with the second talk as well. All right, and with that, I'll hand it over to you, Chris, for a quick lightning talk.
All right, quick lightning talk. I'm not known for quick, that's for sure.
So we
how
have
much time?
We'll have 5 minutes for you.
Okay, and Antje, I sent you a link in WhatsApp, and also I shared a link on the Zoom chat here for accessing the Slack channel. So maybe we could try to keep, and there is a channel over there called May 15, 2023. So let's keep an eye on those things. All right, let me share my screen. And so what am I covering today? I'm just covering the PEFT stuff, is that right?
PEFT, prompt tuning, reinforcement learning from human feedback.
Oh, okay. So yeah, hi everyone. I'm Chris Fregly, Principal Specialist Solution Architect. Been running this meetup for many, many years. I think, Antje, we're up to, I think 2016 or 15 was the first meetup. So I think almost 7 years, something crazy. We've done hundreds and hundreds of these, and we'll post a link to the video. There's a YouTube channel by the same name, Data Science on AWS, so you could check that out. Also, Anjan and I wrote a book that's linked here. We have a GitHub repo that has all the code samples for today out there, and many, many more. Also, all the samples for the book are out there as well too. So this is actually part of a larger deck that I do that I continue to build on and add slides. I think it's up to 83 slides. So obviously we're not going to have time for all 83 slides, but and next month, this is a little teaser for next month where I will be doing this full thing, hopefully in only 30 minutes. Last time I only got through half of it in 1 hour, so I do have to kind of restructure my timing. And let's see, where do we want to start here? Let me get to the to the agenda. Let's see, what's this slide? All right, this is just normal stuff. Why generative AI? It's by now, I think a lot of folks know this. All right, so the full agenda is going to talk starting with pre-training and how to actually start from scratch. Now, it's not something you do normally, but you know, most of the time you will start with an existing pre-trained model, and you will fine-tune it with your own instructions and completions, and so the full talk will actually talk about catastrophic forgetting and chain of thought fine-tuning and all kinds of fun stuff. But this talk's really going to be focused just on just a quick blaze through these these parts here. So let me just copy and paste that right in. Boom. We get to one sufficient. All right. So PEFT. PEFT is sweeping the world. If you're not familiar with performance efficient fine tuning, you can download some papers this week or this weekend or during the holiday weekend, whatever is the next holiday for you. PEFT is a way to perform fine tuning in like very often on large models, but with only a single GPU. Okay, and you still pretty much need GPUs these days to do anything significant. If you do use CPUs, things just take a lot longer. So just be prepared. Anything in this large language world typically does require a GPU. The good news about PEFT is you only need, in a lot of cases, just a single GPU. So magic number here. Well, when do I need to use PEFT, or when at what point do I need to start thinking about GPU RAM, right? Because unlike CPU RAM, which is pretty much unbounded, I mean, bounded to a limit, but with like GPU RAM, these GPUs, the largest right now is the 80 gigabyte. And so, using sort of magic number math here, 1 gigabyte of GPU RAM, you can fit approximately 1 billion parameter model. Now, there's a caveat to that. So this is really easy to remember, but the trick is you have to quantize down to 8-bit, meaning your what would normally be a 32-bit float gets shrunk down into an integer 8. Okay, so might be a little bit out of scope. If it doesn't make sense, or quantization you're not familiar with, we will talk about it more in the full talk. But just know that if you're dealing with the full 32-bit, you actually need 4 gigabytes of GPU RAM for a 1 billion parameter. All right, so let's do some quick math. We know that GPT-3 and Bloom and some of these other ones are 175 billion times 4. So I would need 700 gigabytes of RAM. Now, divided by the largest GPU right now, you would need about 9 GPUs. And just know that you often get clusters of 8. So we are already out by 1. So yeah, anyway, just keep an eye on this math. You will almost always drop down to what's called 16-bit. And that reduces the burden by a little bit. So we do, so now all we need is about 4.5 GPUs at the 80 gigabyte. Now, those 80 gigabytes are pretty tough to get sometimes. And, so if you are planning to use those, just make sure that you work with your cloud provider to say, hey, this is what I need, and I want to pre-provision these and have them run for days and days and days if need be. Now, some of you might also be aware that when you're training, what happened here? I lost my spot. When you're training, so that's just the actual raw parameters. When you're doing any kind of fine tuning or training, you actually have oftentimes four times, even up to 20 times the amount of RAM is needed to actually perform, the back propagation and to, so there's more overhead than just the actual model parameters itself. So keep in mind, sometimes you have to multiply by 4. I've seen cases where we actually have to multiply by 20, which then puts us way out of the range. So 175 times 4 times 20, now I need 14 terabytes of GPU RAM. And it depends on what kind of atom or which kind of optimizer that you're using and some other things. So you will almost always need to use FP16 to at least get it down to half, and then sometimes into 8. All right, so yeah, here's some more numbers there, some more math. So the other option, so what I was describing earlier was loading all of the parameters and being able to train all of the parameters of your large language model. Well, these large language models can be, 175 billion. They can require a massive amount of GPU RAM. So there is this, I guess, field of study, and there's a lot of papers on this, called PEFT, Parameter Efficient Fine Tuning. Everyone calls it PEFT, just accept it. The most common type of PEFT is actually what's called LoRa. And common in terms of my personal experience, I think Antje has similar experience where the AWS customers seem to all be asking about PEFT. Other ones are prompt tuning and prefix tuning. I don't think we're going to have time to talk about those, so maybe let's focus on LoRa and what LoRa is. So let me get right to it. Let me just skip over prompt tuning. Let's get right to LoRa. So LoRa actually, instead of training all of the weights, all 175 billion weights, it can actually make a low rank representation. So think of like one gigantic matrix of all the weights, all the neurons, all the nodes in your neural network. If you can shrink that down to two, think of like singular value decomposition, right? Where you can actually just have two smaller matrices, the rank of which is very, very tiny. Oftentimes rank equals 4. If we can essentially represent all of those weights or certain parts of that neural network with these low rank representation and just train those, and the results are actually quite astonishing here. So we see with a very, very small rank, so rank is 4, so this is very tiny. This is when I use rank 4 on the models I'm training, around 8 billion or so, this comes down to about 0.17% of the trainable parameters. So what does this mean? So this means I can freeze the other, 99.8% of my model's parameters. I don't have to do updates. I don't have to store any of that overhead that's needed to do the back propagation. And all I will end up training is a very, very tiny 0.17%, not 17%, 0.17%. Of that model. This can be trained very quickly, relatively. This can be trained on a single GPU, requires much, much less RAM. And so the base language model, which is 175 billion, for example, that whole thing freezes except for just a tiny bit that's being injected with these low rank. So, here we see pretty good results, comparable results. Even better results when, in some cases, where we use LoRa. Okay, so there's the paper there, very cool paper.
And let's make sure to keep it short, Chris. I know you can talk for hours on this topic, but
okay, yeah, where am I at here? I'm at 5 minutes, okay. It's using a PEFT method, PEFT, okay, and yeah. And then RL, right? That's the other one, real quick, responsible. Yeah, this is pretty much the main slide here. So, and we'll dive much deeper into this. We have a lot of notebooks on this area, but what we're trying to, and the intuition here is that reinforcement learning with human feedback really is dominating the way these models are being fine-tuned these days. So if you're familiar with like, ChatGPT, GPT 3.5, GPT 4, these models have a knowledge cutoff is the term as of like 2021, where they stopped doing the sort of traditional supervised fine tuning. That's this kind of step 1 here. Step 2 is this training a reward model from, with human feedback. So think of like, SageMaker ground truth or some type of, human labeling where people are so humans are presented a prompt and a series of responses. Here we have A, B, C, and D right here in the middle. And the human actually ranks which ones are better. And this is the best for this. And so humans, they are being asked to find the most helpful answer or response, the most honest response, and also the least harmful or the most harmless response. And so that's what's traditionally called triple H, helpful, honest, harmless. And all of that gets fed in, and reinforcement learning is applied, and boom, 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 and out comes a model that is either detoxified or has become more helpful or more honest. So here's a quick screenshot. Angela Merkel's favorite president of the US, George Clinton, who's not even a president, he's a musician, and then Barack Obama. So the user would rank low or high. All of this gets fed in as a reward, and the model is then tuned. Okay, and I think that's it, Antje. The more will come next month.
Right. If you're interested in this topic, join us in next month's meetup, and Chris will dive into much more detail here. All right. And with that, I'll hand it over to Sonali and Anjan. Thanks for joining us today. And you two will tell us a little bit more about intelligent document processing, right?
Sure. Thank you. So today we will talk about, let me share my screen meanwhile also when I talk. So today we will talk about like intelligent document processing, and we will see like how we will use not only the pre-trained AI services as well as generative AI models to process any kind of documents. And documents, it's a good data set we are talking about, like it is unstructured data, most commonly used. So with quick intro, Sonali, I lead the solution architect team for document processing. We have Anjan, Biswas in the call, who will also dive deep into the few short prompt training as well as RAG approach to on the generative AI model and how that can be applied to document processing. With that, let me first quickly give you a high-level overview, like why when we are talking about document processing, what is that, and how AI services can help in document processing. Document processing or intelligent document processing is you all are dealing with papers in this world as well. We have both digital as well as non-digital document type that we are talking about. In that case, how can you get all those insight out of those documents? Can we automate that? When that question comes, you are looking for an automated solution. And that is what intelligent document processing. Here's some customer testimony as well as a why piece of it, like how you can leverage AWS AI services to automate this IDP or intelligent document processing to reduce cost. And we have an in-depth study on the Forrester study here. We are happy to share the link. They with detailed case study, they detail about like there is a 73% on the ROI improvement that they see with AWS IDP. Similarly, we are talking about models. Model accuracy might vary. And we are talking about pre-trained models in this case. And those are some of the AWS AI services, such as Textract, Comprehend, those kind of services, very accurately trained with the right pricing for our customer. So here is a PTM, it's a recent testimony that they went public with, where they talk about how they could get the 97% accuracy using AWS IDP services, not the least. Productivity improvement. When there is a human being review those documents, it gets slowed down. Sometimes there is a high likely chance of error introduction as well. Leveraging those automation, those tools, you can automate that for the productivity improvement. These are the high level basic, but now let's deep dive into like what's IDP, how it looks like. Instead of slide, I'll want to take you through a quick demonstration on how IDP currently looks like with AWS AI services. So this is what is IDP. I'll take you one use case and a quick demo. So insurance use case. Insurance use case, what happens, like you get a lot many paper documents in the package. Can you adjudicate that claim in an automated manner? So the answer is yes. We will try to take an attempt to adjudicate in an automated manner wherever possible. And I'll take you through one such example of a new claim. In the new claim, you see here, like we have a set of documents that have been submitted in the data capture stage. I, as a human being, I have to see like what this document is, open it up, then I'll know what document type is. But in this visual, you will see like, honestly, these documents are submitted through the API and you don't know how to categorize those documents unless you automate that. And let me click this with the next button. Yeah. Let me click this next button in here. And you see this, we leverage a comprehend classification under the hood. It's a model that we have trained with our set of documents, and it can classify those documents now accurately categorized. Here intentionally, you can see here review required. Our models, they give you this confidence threshold, like how confident the models are detecting something or categorizing something. If you're not happy, always have an option for human review. And moreover, let's move on. Documents categorized accurately. Don't stop there. Then next step is like, how can you extract everything from these documents? I'm showing you visually. Honestly, everything is API and you can automate this end-to-end process as well. So here is the claims document. You see like it's a semi-structured as well as a little structural document, like there is key value, there is table in here. So you talk about form API, you can talk about table API and whatnot. If there is a signature present, it can tell you also like, hey, there is a signature, and it will give you the confidence score with the signature. These also insurance ID card, and you will see like this is, I will not dive deep, but you will see like how the structural information from any type of documents is getting extracted with the confidence score from your document type. Similar concept here, but I will talk about these two. In Textract, under the hood, if you want to know like what service we are using, it is Amazon Textract. Amazon Textract also supports like they have specific API for invoice and ID type of document. Here is you are talking about say driver's license document, right? It's not only extract all those things, it will normalize. Normalize means what? Like here, if you see FN is John, like it doesn't say first name, it says FN. We will normalize those things for you. The standardization of the nomenclature that we will do automatically for you so that you don't have to post-process all those documents. Similar concept applies for the invoice and receipt type. We not only extract all the information, we will summarize, we will not only, we will give you the summary field, we will normalize, standardize those fields for you, total, subtotal, tax, those kind of fields as well we will give you from invoice and receipt type of document. So quickly moving on to the next one. What if you have a business critical information, like here in this paragraph of text, somewhere you see the patient ID is there. So can I get that patient ID? I'm just interested in that. Yes, you can. And under the hood, we have train, comprehend, NER model, entity model, and using that, you see like we are able to give the patient ID and whatnot, additional parameters that you train, you can get all those information from your document type. If you have a requirement on the medical side, don't stop. We have comprehend medical. It can give you the ICD-10 CM code, SNOMED city code. It can tell you medication or dosage, all the medical NLP kind of information from your document type. Moving on very quickly to one of the last section, and generative AI has taken this enrichment section of the document processing to the next level, which we will talk about shortly. But in document enrichment, one use case very common across enterprise industry, PHI, redaction, and we leverage comprehend PII comprehend medical PHI to get all those PII, PHI information, redact the sensitive information before even processing. So this is in a nutshell, we walked through like what is IDP or what's the stages of IDP would look like, or intelligent document processing would look like, how you can apply your rules. This is the rules section. Like, hey, all my documents are present or not? Are these information extracted? So you will start backward from these rules and leverage technology to automate your document processing use case. So this is at very high level IDP. And if you want to look at the pipeline, here is the pipeline, like different stages of IDP and what are the AWS services that we currently have to automate this pipeline. You can categorize, you can extract, you can enrich all those documents. Finally, have the human option for the review and verification, where the reinforcement learning can also happen for your leveraging human in the loop. At the next stage, this demonstration that I have shown, leveraging AWS AI services, extract, comprehend medical, where we are going with is leveraging generative AI models. In that case, we have the Jumpstart LLM models as well as a Bedrock model. What the future is changing towards is this foundation models is predominantly text-based. And what we have seen from our customers is like the input modalities is document type. In those cases, can we have all the text from this document and send to our downstream processing for processing? In that case, our foundation model of your choice. So in that case, yes, probably you need an intermediary layer. Probably if you are enterprise customer, security sensitive, and you want like a generally available, highly trustable AI service, go ahead with Amazon Extract, and it can extract entities, text out of your documents, which can be further processed with foundation model or LLM of your choice. Also, we just saw like documents, not necessarily always a paragraph of text. Sometimes there is structural information like table, key value is there. You might want to process those things differently, right? In those cases also, like you have the form you can extract, or you can extract the table along with the structure. There is, of course, definitely paragraph of text. Probably you want to extract, send it to your, again, generative AI model and do the further processing. So you will have a use case when you will expand your use case in the document processing, like you are dealing with both structured, unstructured, as well as blur of text in one or multiple pages of document. We are giving you this architecture or this sample or the options where you can mix and match these AI services as well as LLM to get the result. And Anjan will walk you through and shortly walk you through how it looks like in the demonstration as well. Another very common use case that we are seeing is how can I handle my sensitive information before while working in the scope of the generative AI. So might be they are leveraging any open source model, and they're sensitive about the sensitive information, the PII, PHI information in the documents. No worries. Our customers already using in the production, like extract, comprehend as a combination together. Like you can extract, you can de-identify those sensitive information before even sending to the large language model of your choice for the further training, further fine tuning, as well as getting your answer. So these are the very two common use cases where you can include IDP plus generative AI. But I will hand over to Anjan to show you, like, there are multiple use cases on IDP, Q&A, doc summarization. So instead of me talking about this, I'll let Anjan take you through a quick demonstration as well as the detail of the tuning and drag approach. Anjan, off to you.
And just real quick here, Sonali, while you hand it over to Anjan, we do have a bunch of questions here coming in the chat. So while Anjan is presenting,
Yes.
maybe you can answer some of those here already.
Absolutely.
Thanks.
All right, thank you, Sonali. I'll quickly share my screen. Hopefully it's visible.
Yes.
Yes, okay. All right, so as Sonali mentioned, a whole different set of use cases emerging out of generative AI, and these are just some of them. Most popular one, of course, being a Q&A. We have seen all the chat applications and cool chat tools. So document Q&A, getting answers out of your document. We also have document summarization and classification, entity extraction. We have seen cases where LLMs have been used for entity extraction as well as for entity relationships. Sentiment detection, we have clustering, fast search, intelligent search, and so on and so forth. So a lot of different use cases coming up with IDP, specifically with generative AI. Now, we'll go specifically talk about, how do you get responses out of your models using the documents, right? So some of the techniques, as you probably already know, for a QA type of use case, right, is essentially prompt tuning or prompt engineering, where you provide a particular prompt, or we call it the zero shot, which basically acts as a Q&A. You give it a question and the model tries to answer the question, right? How it answers the question, we'll get to that part. But again, as a LLM, it kind of gives you a wall of text, right? But sometimes you may want the response in a specific way. You want some information, some additional information, so that you can do something with it instead of just a wall of text. And that's where, one shot or few shot prompt tuning or prompt engineering comes into picture, where you give the model an instruction and you show it an example of a question and an answer. For in this case, for example, we want the model to also give us the reference, which is basically the page number in a document. For example, it's any company's 10K filing, and we have a question, was the company's financial risk factors? It kind of gave an answer with zero shot, but now we want to know where it gave that answer from. Maybe we want to do, more processing on that particular page. So we showed an example to the model, and where the model basically, we instructed it to give it the page source. Now, how this page source is included in the response, that is, through metadata. We'll touch upon it a little bit when we talk about RAG and Realm in the next slide. But essentially, what you see here in the one shot or few shot example is you get the answer, you also get the source of the page. So it's basically instructing the model to give you an answer. Now, this is all great, right? But we all know large language models, they are large. They have a world knowledge. We call it the world knowledge, or its worldview. They know a lot of things. But in most of our use cases for IDPs, we want the model to stay within the context of the document itself, right? There's probably not a whole lot of use cases where you will see someone, wanting the model to go out and, get information from its world knowledge, because we don't know whether it's going to be, right or wrong, whether it's going to hallucinate or not. So we want the model to be strictly within the context of the document. In this case, it's 125 or maybe 150 page 10K filing document. First of all, that's a lot. That's a lot of pages. That's a lot of text. So, and we have, token limits with the model. And we want the model to stay within that context. So how do we even do that? So these are some of the challenges that we have, right? How do we handle large documents with a model? We want to get answers out of our question from a huge document. We have to deal with token limits. We have to deal with hallucination. We want accurate information from within the document without the model making something up, because it has a huge and vast, knowledge base, right? Which is the world knowledge. So essentially, to address some of this, the paper called RAG, or Retrieval Augmented Generation, came out. I should have put the archive link over here, but if you search for RAG, you'll see that paper. And essentially, this paper talks exactly about this problem, right? If we have a document which is very knowledge intensive, like a 10K filing, and we want specific answer out of that document, how do we deal with all the world knowledge of a foundation model and keep the model within the context of the document? What this paper essentially says, the technique of RAG, is we basically build a context. We instruct the model to stay within that context, and we ask questions to the model and instruct it to specifically keep that context while answering the question. Now, this is a multi-step process. So in IDP, you can think about a 150-page document where you extract text, structural, semi-structural, like Sonali mentioned, out of all the pages. What you would do essentially is then you would perform embedding on all of that text. Once you have generated the embeddings, you would store that embeddings in a data store. You don't want to run embedding, over and over again. Once you generate the embeddings, you store it in a vector database, for example. Now that you have your knowledge base, quote unquote, in the vector database, you can generate the context. So how does the context generation happen? And this is where the concept of retriever comes into picture. Retriever is essentially something that takes the question from the user. It generates embedding from the prompts, and then it does a similarity search from the vector database. Now, you can do the similarity search on the entirety of your vector database, but in most of the cases, in our case, for example, I want to only look at the collection which is specific to that particular document. And vector database has collection concept where you can isolate separate collections of it, right? So you can run similarity search, and there are different ways of running similarity search. One is the basic similarity search, where the vector database will return the parts of the text from the document that are relevant to the question. There's max marginal relevancy search as well that you can use. But essentially what it does is it gives you that specific pieces of information from that document, which helps you build that context for the model. And you're specifically instructing the model here, like, hey, this is my prompt, this is the question or the query, and here's the context. Do not go beyond the context. I want the answer from within this context. I don't want you to tap into your world knowledge, because I'm not quite sure whether you're going to give me a right answer or a wrong answer. I want you to stay within this context of the document and give me the answer to this question. So, and then once you have build that essentially prompt and examples using your generated context, you give it to the model gives you a response. So essentially that's RAG. There's also another concept called as Realm. I encourage you to go online and check it out. And we have a quick demo of what IDP may look like with the Q&A. I'm going to quickly run you through that demo here. Redaction, Sonali has mentioned about redaction, where you take the text out of a document and you perform redaction. Here you see a bunch of PII information is there. So we have redacted all of that information using AI services, which is Comprehend, and we don't want any of those personal information because we are running it through a model. Perhaps that's our business policy. We'll jump into the Q&A because it's probably the most interesting part here. Now we have a document that is about 6 pages, essentially, and we want some question answered out of this whole set of pages. So we have some questions. So let's ask a question. In this case, was the patient's social history, and the model essentially generates that answer back for that particular page. Let's go with the insurance ID. Now, as you can see, the page changes, which means the model actually is responding with the source of where it's generating that answer from. It gave me the insurance ID from page 5 of that multi-page document. So, and this is how we are doing. Like in the back end, we are running it through this context generation. We're instructing the model to give us context give us where it's getting the answer from, and essentially answer the question. Don't go beyond what you know. Don't go beyond the context that was provided to the model, essentially, and it follows that. I'll run through a few more examples. For example, here in this case, it's a provider doctor's notes, and the model actually found the answer to this question from that particular page, and it responded back with that response, and it showed us the page as well. So that's one of the use cases. Again, we also ran summary. Summarization is a big problem with LLM, especially with large documents, and you have token limits. You cannot really summarize 500-page document in one shot. You have to do, you either do page summaries, you take those summaries, you combine them, and then you generate summaries of summaries. For example, in this case, it's a 6-page document, and we generated summaries for each of those pages. You can take it a step further, combine all of these summaries from the large language model, and essentially provide it to the model back again so that it can generate a much shorter summary of a huge or large document. So this is where doc Q&A, doc summarization, entity extraction, and so on and so forth, with provided context limited to the context of the document comes into picture with generative model. And as you've seen, some of our AI services like TextTrack is able to help extract the text out of the document, whether in structured or unstructured way, as well as do things like PII redaction with Amazon Comprehend and so forth. So that's essentially intelligent document processing and how you can make it work with generative AI and some of your generative AI use cases. And then with that, I'm going to hand it over to our next speaker, or I'm going to hand it over to Antje.
Yes, thanks so much, Anjan and Sonali. We have a ton of questions in the chat, so if you can just help answering those, folks are really interested, understanding it more, talking a little bit about the embeddings here and use cases. So if you could help answering, and in the interest of time, I'll hand it over to our next speaker, Dilshad. We're switching topics a little bit and going back to reinforcement learning. And super excited to see your slides and demo on this. Do you have a demo?
I have a code walkthrough. Let me.
Nice. Yeah.
Is my screen visible?
Yes. And just a quick note to everyone, in case we're running a little bit over, no worries. We keep recording here. So we want to make sure we get all of the great insights here from Dilshad in his talk. Thanks so much. Yeah, take it away.
Thank you. Thank you, Anjan. So my name is Dilshad. I am a data scientist with AWS ProServe. I will be talking about how to solve a portfolio optimization problem using reinforcement learning with Ray and Amazon SageMaker. Brief outline about my talk here today. I will introduce the specific portfolio optimization problem, the parameters involved, and some constraints that we would like to consider when solving this optimization problem. And then we will have a quick refresher on reinforcement learning, just to get an idea of how a reinforcement learning model is usually trained. And then I will talk about action masking, which is kind of like the main theme of my talk here today. What we will do then is to solve this portfolio optimization problem using reinforcement learning with action masking. And then the solution stack that we will use, I'll talk about that when we implement the solution, and then we will do a code demo to see how it is actually implemented. Let's get started. So the particular portfolio optimization problem that we are looking at involves basically an investor who would like to trade multiple asset types with the goal of maximizing their total portfolio value. Now, we're all familiar with this kind of problem in our own personal finance journey, when we would like to trade stocks year after every year, and then we would like to keep our portfolio healthy and keep a profit. For this particular scenario, the investor has access to 3 different asset types and a cash balance. You can think of these as like 3 stocks, for example. This could be your Tesla, Google, and Apple. And they also have a cash balance. And the investor goes to an agent who will solve the portfolio optimization problem for them. And what the agent has to do is that during each investment period, the agent has to decide how much of each of these securities, each of these assets they're going to buy or sell. And to purchase any asset, the agent will use the cash balance. So this is like a bare bones structure of a standard portfolio optimization problem. Now, what we're going to do, we'll try to make it a bit more realistic because we know that in reality, we cannot buy and sell as much as we would like. There are usually constraints on what kind of transactions are possible. So what we will do is to introduce a bunch of constraints, and these constraints will be like functions of how much cash you have, because obviously if you don't have any money, you cannot buy anything. What is your current total portfolio value, and the number and types of different assets that you have and their current market value. Let's look at the constraints that we are trying to incorporate. So the first constraint I have here is that if the agent looks at the brokerage account of this particular investor and they see that they have a certain number of assets for a particular type, let's say they have 100 stocks of Apple, then obviously the agent cannot sell more than 100 units of Apple at that point in time, because you cannot sell what you don't have, right? You can only sell up to what you already own. So that, which is quite evident. So obviously this constraint has to be respected. So that's constraint 1. Constraint 2, here things get a bit more interesting. The investor thinks that asset 3 is highly volatile. You can think asset 3 is, say, like Bitcoin, it fluctuates a lot. So they want to limit their exposure to this volatile asset. So what they tell the agent is that, you know what, I don't want the contribution from asset 3 to my total portfolio value to exceed a third. So if, let's say, your total portfolio value is $900 and you have $400 of market value in asset 3, then the investor says, don't buy any more of asset 3 until that, it's less than 1/3 again. Now, that being said, the investor is not super risk averse. Investor actually has a moderate risk preference. So they say that, okay, well, I don't want too much of asset 3. At the same time, asset 2 is kind of like a conservative buy. It does not have a lot of upside. So don't buy too much of asset 2 either. So if your contribution from asset 2 crosses 2/3 of your total portfolio, stop buying asset 2. And finally, the final constraint is that the agent cannot buy any assets if its current cash balance is less than $1 US, because you need money to buy assets. So if your money drops below $1 US, then you have to sell some of the assets to actually get the money to finance your next purchase. So these are the 4 constraints that we would like to enforce. So just a quick recap, we have 3 assets, we have some cash balance, and we have 4 constraints that we would like to enforce. And the agent has to buy or sell these assets to maximize the total portfolio value. And what we're going to do is to try to solve this using reinforcement learning. So next slide, let's look at what a typical RL problem looks like and what the RL training actually accomplishes. So reinforcement learning, or RL, is the go-to machine learning technique if you want to solve a sequential decision-making problem, like the one we just saw. The objective is to get the optimal sequence of actions that maximize a reward signal. So here we have a standard reinforcement learning scenario. Let's say we have an intelligent agent or an agent that's ready to be intelligent. And this agent can observe its environment. In the context of the portfolio optimization problem that we just discussed, the environment could be the market, like the current market price, and the current state of your brokerage account. So the agent can see that, and then based on that, agent can take actions. For example, agent sees that they currently own no Apple stocks, and then they look at the market and then think that, oh, our Apple stocks are actually undervalued. So then the agent takes an action, and then the state transitions from the current state to the next state, where let's say if the agent buys 80 Apple stocks, in your new state, you have your brokerage account now looks different, because now there's like Apple stocks involved there. And in this process, if you're making a good action, you'll also get a reward, which I have here as RT+1. So the idea then is that during training, the agent will repeatedly take actions and then observe the rewards. Now, the way the agent takes actions is based on something called a policy. The policy is a probability distribution, essentially the conditional distribution of the actions conditioned on the state. The idea then is that by repeatedly taking actions and observing the rewards, we can gradually update the policy, help the agents make better actions and learn a better policy. Ultimately learning the optimal policy which will maximize the reward over the entire horizon of an episode. So that is what reinforcement learning accomplishes. Now, let's bring in constraints back. Remember how we discussed that we wanted to solve a portfolio optimization problem with 4 constraints. So here we cannot simply choose the optimal actions to maximize reward, but we also have to respect the constraints. So just like how we saw in the portfolio optimization problem, quite often the actions that you can take will be constrained based on the state that you're currently in. For example, we saw that if your current state has only 120 Apple stocks, you cannot take the action which involves selling 150 Apple stocks. That's not allowed, right? So then the question is, how do we incorporate these constraints in your reinforcement learning training? So the easiest answer, kind of like a brute force idea, then is to simply let the agent randomly sample these actions and then give huge negative penalties for sampling any bad action, any actions that violate constraints. But this is horribly inefficient because then you have to basically sample a lot of bad actions for a really long time before the agent even learns to know that, okay, these are bad actions and I shouldn't even take this, before it even starts to learn what are the optimal actions among the good actions. So action masking is actually a solution to do this in a more efficient manner. The idea here is that we will append the state variables from the environment with what are called as mask variables. The masking variables, these encode information about which actions actually violate the constraints. So the policy actually becomes a conditional distribution where the actions are conditioned both on the state and the masking variables. So as a result, when the agent takes an action, the environment transition, the only actions the agent will take are going to be the actions that are admissible under the constraints, and the environment will transition to its next state. And then the masking variables will also transition because obviously when state changes, you might have new actions that are now admissible or that are no longer admissible. That's the idea behind action masking. So the next step for us then is to try and see how we can implement this. So to solve the portfolio optimization problem. So let me just quickly discuss the solution stack that we have. There are 2 pieces to this. One is the Amazon SageMaker, specifically SageMaker RL. The other is Ray. Amazon SageMaker, as you know, is the Amazon's solution for managed machine learning workloads on the cloud. It basically supports a lot of different tooling, end-to-end workflows and pipelines. And Amazon SageMaker RL is the specific service from SageMaker to support reinforcement learning model training. And it also offers a lot of customizability. You can train your models distributed or on a single machine, locally or remote. It has supports for a lot of different types of environments, and also allows you to try a lot of different types of reinforcement learning algorithms. So that's one aspect. The other aspect is Ray RLHF. Now, Ray is an open source Python project to develop high performance distributed Python applications. RLHF is the reinforcement learning toolkit, which comes as part of the Ray project. So RLHF makes use of Ray's abilities to distribute workloads to train distributed reinforcement learning workloads, which makes it really easy for us to experiment with different RL workloads. And also it comes with support for a really large number of pre-written reinforcement learning algorithms so that we can essentially use them in a plug and play fashion. So these are the 2 things that we will use, Ray RLHF and Amazon SageMaker RL. So now I'm gonna share my screen on SageMaker Studio so that we can look at some code where we have implemented this. Give me one moment. Okay. So here I am in Amazon SageMaker Studio, and I want to bring your attention to 3 pieces of 3 Python modules here. One is the mask model, where we will implement action masking. Then there's the trading module, where we implement the trading environment, where all of the portfolio optimization and stock trading happens. Then there's the training configuration. This is the training configurations that Ray will pass to Amazon SageMaker to train the machine learning model. So let's start with the trading environment. So this trading environment is actually involves a class, that is a subclass from Gym, OpenAI Gym. And this class has 3 modules. There's an init module, there's a reset module, and a step module. Init, as you can imagine, is where you initialize all your parameters. So for example, here I'm initializing some parameters for randomly sampling my asset prices. What I want to bring your attention to here are these 2 lines, the action space and observation space. The action space describes the structure of your actions. So you can see that it's a tuple with 3 elements. This means that you actually have a 3-dimensional action vector and a vector with 3 components, where each component can take 11 possible values, 11 discrete possible values. That's what this line here is specifying. So what are these 11 values? Let's go back to the slide here. So the action vector has 3 components, as I said, and each component represents your action, the trade action for each of these 3 asset types, right? So of these 11 values, actions from 0 to 5 are essentially your sell actions. So if your A1, the first component, is action number 2, then that means that you're going to sell 30 units of that particular asset. On the other hand, if you choose 9, then you're going to buy 40 units of that action. And if you choose action number 5, you're going to keep holding. So just keep this in mind, that actions from 0 to 5 are sell, and actions 5 onwards are buy. Let's go back. So that's the action space. Then there's the observation space. Recall how I mentioned that we will append the state with the masking variables. That's what's happening here. We have a dictionary state where we have the, if you don't have an action masking, it will just have this trading state. But since we are using masking, we'll append that as well. That's with the init method. Now let's look at the reset method. This method gets called at the beginning of every experiment. So what happens is that in the beginning, all of your brokerage account essentially becomes 0. Like you don't have any assets, right? You just have some money. You have a cash balance of $1,000. And using this $1,000 over the next several time periods, you're going to buy different assets, buy and sell them. That's the idea here. So what we do, we randomly sample some asset prices, and then we create a state. The state consists of how many assets you own, which basically at this point is 0, 0, 0. And then your balance is like $1,000 and the price that you sampled. And then we call this update mask method. This is where we calculate the masking variables. Let's go down to see how that is implemented. So the update mask method, it evaluates each of the 4 constraints that we mentioned earlier. Initially, it sets all of the mask values to be equal to 1. Then it evaluates, let's say, constraint 4. Constraint 4 was that if your balance drops below $1, then you should not be able to buy anything, right? You should be selling some security, some asset to actually get the money to finance your purchases. So that constraint is implemented here. We check if balance is less than 1, and then see that we are setting the masks for all of the actions starting from 6. These are your buy actions. Their masks are all set to equal to 0. Similarly, we have constraint number 2 here, which checks whether your contribution from asset number 3 is crossing that 1/3 threshold. If that crosses, then you set buy action, the masks for the buy action for asset 3 equal to 0. And same for the other 2 constraints as well. So that way we calculate the masking variables depending on your current portfolio value and current asset holdings. And then you have the step method. Here we sample each action during the training. And then what we do is that if your action is less than 5, which means that you're going to sell, then you update your assets. Because you're selling, your assets decreases. Your balance increases because when you sell something, you get more money. If the assets are greater, if your action is greater than 5, then you're buying, your assets increases, but your balance decreases. And we recalculate our masks, and also we calculate what's the total price of the assets that you hold, which is basically the sum of the cash plus the market price of your assets multiplied by the number of assets that you hold. And then your reward is given at the end of the whole training, which is your total portfolio value. That's what we have in the environment. Now let's look at the masking model and how action masking actually is implemented. So this is a parametric action model, which basically means that you're able to use a TensorFlow model and then parameterize it. So what I want you to focus on are essentially this part, the action embedding model and this forward method. This is an embedding model that takes your states as the input and emits the logics for each of the actions. So the outputs of the action embedding model, you can send that to a softmax function, and then it will give you the probability with which you can sample each of these different actions. That's what happens usually. Now, what we do is that we bring in the action mask values here, and then we modify the value of action embedding by this number called logit modifier. The logit modifier is calculated as the logarithm of the action mask values. So remember, for any actions that violate constraints, we set their masks equal to 0. What is the logarithm of 0? It's like negative a huge number. So your action embedding gets basically added to a negative huge number. And when that goes to softmax, it's e raised to a negative huge number, which quickly goes to 0. So your sampling probability of actions that violate the constraints drop down to 0. Basically, you don't end up sampling any actions that violate the constraints. That's how the masking is implemented. Now, to see if this is actually working as expected, I have a test notebook here. I'm not going to go through the whole thing, but what I'm going to show here is that we have a PPO, a reinforcement learning agent initialized here. We also have an environment, the training environment also initialized. Then we call the reset method. And recall how I said that in the beginning, you only have 0 assets in each of your asset buckets. You haven't bought anything. You just have a $1,000 balance. Then you check your action mask values. You see that for each actions, the first 5 values of the mask are set to 0 because you can't sell anything. When you don't own anything, you can't sell anything. Next, we will see if this indeed means that, an action's mask actually being 0 indeed means that you're not going to sample it. For this, what I do, I extract this action mask out of the state and then set all of the mask values equal to 0. Then for the first component of the action vector, I set action mask equals 1 for the 8th discrete action, for the second component for the 5th discrete action, and for the third, either 1 or 2. And then I randomly sample an action after setting these mask values, and we see that it sampled 8, 5, and 1. These are the only actions. 8. So this could only sample 2 possible actions: 8, 5, 1 or 8, 5, 2, and it sampled 8, 5, 1. So this way we can be sure that yes, indeed, the constraints were actually respected. So the final piece then is the, excuse me. My session was expiring. Sorry about that. The final piece is the training configuration. The training configuration is where we describe what training parameters to use. So this is really like an interface between RLHF and SageMaker RL, right? So here we describe what reinforcement learning algorithm we want to use. I say PPO, and I want to train 500,000 episodes. And then I don't want to use PyTorch, I'm going to use TensorFlow for this. My learning rate, the custom action masking model, that I'm going to use that, and I'm going to use stochastic sampling as my exploration configuration. So once we have specified all of these things, then we can go to the training notebook and then call SageMaker RL just like how we usually call any SageMaker estimator. Again, since we're past time, I'm going to quickly go through this. So we have this RL estimator where we specify the training entry point. The training entry point is the training config that we just mentioned earlier. So we specify that, we specify the Docker image that we will be using, and SageMaker RL comes with pre-built array containers so that we can simply specify the image name, and then we will be able to train these reinforcement learning models using that. And then we call estimator.fit, and that will train our machine learning model. And I have one slide here that shows what we observed. So this is the mean reward per episode. If you recall, our reward is basically the total portfolio value at the end of the 20 investment periods. So we start with $1,000 cash balance, and as the agent learns, we basically end up gradually with about $3,300 worth of portfolio. That's everything I have. Thank you so much for listening.
Hey, yeah, Antje, you're on mute.
Sorry about that. We do have a question here, Dilshad. The masking, is it to help to train faster by decreasing the number of available actions, or is it to intend to impose constraints?
It's to avoid sampling any actions that violate the constraints, because by nature, the training usually happens by randomly sampling actions. And when we have any machine learning model, we know that our initial neural network parameters are completely random. So any action can be sampled. So in theory, we can give a huge negative penalty, as I mentioned in the beginning, and then make the network learn to not take those actions, but that just makes learning really, really slow. But in this way, we can make sure that you're not going to sample any bad actions, any actions that violate the constraint.
Okay, and that is because masking was applied on the result, not during training.
It is applied during training. So
Okay.
that's the neural network. It's just that masking, the idea is that the agent learns not to take bad actions, not through rewards, but by the structure of the neural network itself. Because the policy itself is parameterized by the masks, so that it doesn't have to see the rewards to learn to not take the bad actions. So.
All right, and we shared the link to your blog post. So I think for folks, if they want to reread about it and follow the links there, right, to the GitHub repo for the sample code as well. So we shared those in the chat.
Yeah, Dilshad, while we have you, if you have an extra minute, can you like describe the intuition behind PPO? And like, why did you choose PPO?
Oh, the reason why we chose PPO is primarily because it's number one, it's a workhorse compared to compared to a lot of other algorithms like DQN or DDPG. When I was training this model, what I observed is that DQN is actually extremely slow. Usually, typically that we see with the value-based algorithms, and with DDPG, another policy-based algorithm, what we saw was that training was actually becoming unstable. So one practical tip that I have seen after training many reinforcement learning models is that some of the algorithms require extensive tuning of your reward function to make training stable. Others are a lot easier to make things stable. And PPO is actually one of those things where I've seen I don't have to work really hard to get my reward function to have like a certain shape for things to converge, as opposed to a lot of them.
Is PPO like more parallelizable than some of the other techniques?
I don't think so. I'm not sure. I don't think there's any difference in that sense, because ultimately you are collecting experiences, and the neural network is just being trained using the experiences, and the neural network part can be completely put on a GPU, and your simulation can be kept on a CPU. So I don't think that issue is there.
Okay. Okay. Awesome. Yeah, thanks so much, man. Yeah, Antje, do we have any other PPO as a black box or not? So, and you were using the Ray PPO?
Yes. So
okay.
Here, so that's like, again, the benefits of using a reinforcement learning toolkit is that you can use them, plug and play, quickly experiment so that you don't have to write anything from scratch.
Okay. Awesome stuff. A lot of questions today, Antje.
I know,
yeah.
Let's get to the last one here and then we'll wrap it up maybe. Can I use this approach of action masking in reinforcement learning with other problem types outside of portfolio optimization?
100%. So actually, we implemented this for one of our customers. It was in the financial services domain, but not for portfolio optimization. So you can, for example, if you want to, and let's actually go out of financial services completely. Let's see, if you want to have an autonomous robot that wants to navigate, and then let's say it's like it has to go through a course, and the course, let's say, has a neighborhood where there's a speed limit, and this robot has to choose from its speed levels. And then if you have a constraint there on what you can do, how much acceleration is possible, then you can implement this. That'll be like a quick example where it will be useful.
All right, perfect. Yeah, thanks so much, Dilshad, and thanks also to Anjan and Sonali. I think Anjan went and answered all of the questions here we had in the Slack. Thanks, everyone. Thanks to our speakers, and thanks, everyone, for joining today and sticking around. See you next month.
Right, thank you.
Bye. Thank you.
Thanks. Bye-bye.